I'll just go ahead and show you some stuff. Ramda is a library in JavaScript that lets you kind of cater to the functional style. Now, you've probably already seen Lodash and underscore before, and so have some familiarity with at least the idea of doing map and reduce and filter and some of that stuff. So that's all here, but there's a couple of differences which I want to kind of highlight in my Ramda demo. The demo, this guy. So one thing, let's do a quick refresher on closures and currying, because that's at the heart of this Ramda design philosophy. We want to create functional pipelines where the inputs turn into outputs, and then those outputs are the new inputs to the next function. And in order to facilitate that, we're going to have our parameters are going to be automatically curried by the Ramda library. Well, I'm going to just kind of remind you what that is. So say we have this add3 function, and now it's going to take an a parameter. This is the ES6 syntax too, by the way, in case anyone hasn't seen it, but I assume that's not a new thing. So, so a function that takes an a, let's say I were to then to have a function that took a b, and then finally a function that took a c. These are nested functions where I have a closure open. So the inner function that takes the c there can still reach up and get at the b and get at the a. Because and then let's say that once I'm inside, I add them all together. Oh, here, just so we can see what's going on, we'll run a test. Okay. So if I were to add 1 and 2 and 3, then that should come out equaling 6. That doesn't equal 5. Yeah, okay, equals 6. So this is just a reminder. So this is a little tedious to curry your own parameters, I guess, in the sense that you have a function that returns a function that returns a function, and then once you've given all 3 parameters, now we can finally do something at the end. But we've kept closures open along the way so that we can keep state around. And the idea is that you don't have to do it all at once. So if I had like has 1 needs 2 more, could be the add3 where I lock in a 1, and then if I were to take that later at some other point in my life, run the 2 and the 3 on it, that'll still equal 6. So you can delay the arrival of parameters. You could even be something asynchronous that needs to go fetch and come back with, but you might have had another value right away. So it's really just a mix and match to when you got everything, whenever that is, run the computation that you need to run.
Can you use just a couple of the parameters?
Sure. If you didn't need to like use all of them, but then if you didn't need them in the first place, then maybe you would edit your code to just not even have them, I guess, just to keep it as little as possible behind. But yeah, sure you can. So the Ramda library, which we haven't used yet, is going to just make this style of coding a little more convenient for us. So what we would do is we have the same add3, but I'm going to use r.curry, and it's just a single function, abc, that now returns a plus b plus c. Oh, I forgot my arrow. Yeah. Okay, so this is just going to automatically curry each of the parameters, whether I choose to send them. Right now I'm sending them 1 at a time down here, but I could also, if I wanted, send the 1 and the 2 first, followed by the 3. I could send the 1 and then the 2 and the 3. Or if I really wanted, I could just hand all of them at once, and it all works. So that's the automatic currying of Ramda, and that's at the heart of this. And everything we do, keep in mind that the functions have their parameters curried. So I can give it, if it needs 2 arguments, I can just give it the first one, and now it's a function that takes the second one. Or if I really want, I can just give it both arguments, and then it'll just run. So we kind of have to keep that in mind as we go. So that's the refresher on currying and closures that I wanted to give you before we show off some functional pipeline ideas. So let's move to that one. Okay, so to compose a function, we would take, like I mentioned earlier, we have one function that we send an input in, we get an output out, and now that output is the new input to a new function. It's kind of like from math class way back when, if we have your f of g of x, where really we have y is equal to g of x, and then later at some point we're going to take f of y. So g is one function. Oops, too many parentheses there. So if I had a function f that takes an x that's an x plus 1, and a function g that takes an x, and that's, let's say, x times 5, then my idea is I'm going to take my first input and put it through g, and then take that output and put it through f, and then I'm going to have what I want in my hand. So I've just composed those functions together. So if you were to see, if I ran f of g of 1, that would run g first, so we'd have the 1 times the 5, which is 5, and then we'd run f, which would add a 1 to it, so we'd have 6. So that should equal 6. Okay. But if we did them backwards, the order of the function invocation would change what function got ran first. So if we ran f first, then that would first add the number 1, and then we would times it by 5, so we'd end up with a 10 in that position, or in that case. And let me just see that it actually doesn't, I'm not lying that these things actually pass the test here. So again, this kind of functional composition is what the goal of Ramda is you want to create a pipeline where you start with some input and you want to get to some output, and there may be X number of steps in between, where each step can be very clean and single responsibility to just take this input, transform it some way, and produce this output. So then we use the Ramda methods. If I have r.compose f of g, and I send the 1 through, that'll equal to 6. If I have the same g with the f, that'll equal to 10. But we as programmers do not like to think right to left, like because the inner function runs first and then the outer function runs. So in that case, they have pipe. Pipe is just exactly backwards from compose, where we think left to right now. If I did a pipe f to g, well, actually I would say if I piped g to f, then it's going to be the same thing. Oh, we'll put the 1 in. For that same 6 right there. Those two go together. And then that guy, if I pipe the f to the g 1, then that'll equal to 10. So these two methods, compose and pipe, you'll see me use pipe most of the time because that's the one we like to think left to right about. And all of the functional pipelines I'm going to be making for the things I'm going to show you today, I'm going to use pipe. So just a real kind of quick one. Let's say I want to multiply evens is a function that I want to make. So I'm going to go ahead and pipe, and I'll start it with just an identity function. Anyone know what the identity function already does? It's just the function that you give it something and it gives it right back to you. It seems kind of useless at first, but it's really just a placeholder kind of function. Or it's a primitive that you would kind of build up stronger functions out of. But I like to start there when I'm first thinking about a problem. So let's say I want to multiply evens on 1 to 5. And what should that equal? 8. It's not going to pass right now. Oh, multiply evens. Okay. So first of all, we need to filter down to the evens. So that's easy. If we make an isEven function, we have just the modulo 2 thing that everybody already has seen 1,000 times to get even numbers. And then we were to filter to isEven. Now you can see my output has brought my numbers down to at least the even numbers. In the right, you can never see this output right here. So I'm piping, first I'm taking an array of numbers, sending it through this pipeline. The first thing the pipeline is going to do is even. And then next I need to multiply them all, which I can do with a reduce, which will just multiply, and then the seed is 1. Multiply, spell that right. The idea of a reduce in functional programming, if you have a list of things and you just want to end up with one value, you would collapse that list down into whatever value The idea is you have an accumulator function that gets to visit each item of the list, but he brings along with him the state that you've accumulated as you visited each item in the list. So it gives you an opportunity to scoop up things and then produce an output. That's what I'm doing here. So that's the idea of a functional pipeline. Now I want to show you some real life examples or semi-real life examples. Let's say you're on the job and you have some output from the database. I've got some test JSON data that I scooped up off the internet. So this is an array that has 5 objects in it. They're pretty easy. They just have a couple properties like is active on there. We got a name, but it's not just a name string. It's got like an object with 2 more properties underneath it, and some email and some tags. This is because I want to just do some tasks real quick with Ramda to show you how you might solve these problems. You can solve these problems with other styles of programming just fine, but I find that the Ramda code comes out pretty short and elegant. If you're familiar with functional programming, it's okay to read, I think, but then if you're not, you might think it's illegible, but we'll see. So back here on the examples, here I'm gonna start this one off. So my goal is, given that JSON list I just showed you, I'm going to filter this list down to people where is active is true and their age is over 30. And we'll show you how you can build these predicates up and then compose them together in a way that scales very well with large amounts of code, and then lets you not tangle up everything in one method. So I already have the assertions in here just for time's sake, and then I'm just going to show you. I have every function started off with the identity function, which, if you recall, just gives you right back what you have. And now I'm going to actually make it work. So we need a predicate that can filter for is active. So is active would choose the prop equal is active is true. And then we're going to need a predicate for the age over 30. So we'll call it over 30. And this one I'm going to pipe. I'm going to take the property age, piped through this function. It checks if the age is over 30. Okay. Now for the actual method called active over 30, which we're going to use, I need, and it's not just the people. I need to map them into their first names only. That's this test assertion, is I want only the first names of the people who pass these predicates. So I will first, I guess we'll pipe that through, we'll start with a filter. And I'm using 2 predicates, so I'll use the both method, and I'll say is active and over 30. And you can see that narrows my list down on the right to people that pass both these predicates. I could have 100 predicates and just combine them with the r.allPass, and that way I have separately 100 methods that each take an item and return a bool, but then I can compose them all together into one giant single function that just filters all 100 predicates at once. The idea of composing the function is that you don't want to filter more than once, because you would have to iterate the list more than once. So ideally we iterate the list once, and then we just run whatever function we have on each item. So we make one pass over the list. Functional programming can, if you just do filter after filter after filter without composing all your predicates together, you're actually just iterating that list over and over and over, which, if that's, say that's like a huge list, that can increase the expense of what you're doing. So that's just kind of some of the mentality behind why you would try to compose the functions instead of filtering again and again. So then, I need to get the first names. So once I've got that down, I'll go ahead and map them into, I need to get down into the path of their name and then their first name. And that will get me my Patterson, which is who I was looking for. So that is an example. This is what a little bit of Ramda code might look like if you were filtering this list to grab the first names. So let's go ahead and move on to another one. So down here, my next task is to reject anybody that has excluded tags. And I'm saying that excluded tags is this one. And to show you the JSON data again, everybody has tags. That's the excluded tag, is pro-ident. So we've got 3 people that have it and 2 people that don't, looks like. So my test assertion is just saying I should have a length of 2 when I'm done. So let's see if we can get that job done. So in this case, what does it mean to have an excluded tag? I can make a is excluded tag function. It takes a tag, and I can check if any equal that tag in the excluded tags list. Oops, excluded tags. Kind of getting cut off a little there. There we go. So I'm going to use that function to help me check a tag to see if it's in the excluded tags list. And now to filter excluded tags, filter has an opposite, which is called reject. So if you kind of are looking through things and when the predicate returns false, that's when you want to keep them. That's backwards from filter. So we'll just use reject in this case. So r.reject, and items I have are just objects, but I really need to get their tags out. So I'm going to pipe the tags into whether any of those tags are excluded tags. And that ends up being what my method looks like to do that. So this would be like, I have an array of things where each item in them I have to check if there's any of those in this other array of things. So it's kind of like a nested or 2 contains going on, if you can think of it that way. But in this sense, so the objects come through. And if, by the way, when you're building these pipelines, in order to check what's going on at each individual step, you can just kind of throw in like a tap with this log, and you can see the output on the right. So you can check what it looks like as it passes each step in your pipeline. Just kind of when you're, if it's not quite right, you're just trying to tweak it. This is a way you can get some feedback. So if you see up here, if I tap there, those are the objects. If I tap there, now they're turned into their tags. If I tap after that, now they're, oh, I guess our comma's missing. Now they're the true, 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 false, false. So tap doesn't alter the output. It just gives you a chance to check it, and then it immediately returns what it already was. So it can be kind of useful. So let's move on to another one. Let's send emails to everybody. So everyone in here has an email, and my job is to scoop them all up, make them into something I could click on, like say an href of an A tag on a website, so you can just mail to that person. So here we have this make email href method that needs to end up looking like that. That's our goal. So what I would do is I would first pipe them into their email addresses. Oh, I need to, let's see, map. Okay, yeah, I'm gonna map that. Map them into their property of the email address. And now you can see that I have an array of the email addresses. And then next step would be to join those with a semicolon. So now I have a string with all the email addresses joined by a semicolon. And then I need to slap that mail to colon on the front of it. So I'll pipe that into this concat mail to colon. And then there I have it. So that's how I would do that with Ramda for this guy. So then another one, just because I think it's cool, say my job was to take all the possible sums of some numbers. So let's say I had these 3 arrays, and my job is to take the sum of 1 and 4 and 7, like this column, the sum of 1 and 4 and 8. So there's all permutations across these arrays. I want to just figure out what all the sums are. And you can do this with 3 nested for loops just fine. But Ramda has this lift, which lift is more of an advanced one that I won't go over too much. But if I have a, let's say I have a function that just takes the single items A, B, and C and adds them all like that. Oh, did I move? only. There it is. Whoops. Okay, so you don't use this function very often, but if you ever have, the idea is that everything I pass in this array here is going to become a possible A value for this function that takes 3 right here. And it'll do all the permutations across them. But that's just, I thought it was fancy, so I wanted to show you. But now I'm going to move on to a different example, which I think we still have time for. I have a square code challenge for us. This is just something I scooped up off the internet, and it's a basic problem to solve for people coming out of school. They say it's easy. I didn't think it's that easy, but we'll see. So the idea is that we are going to encode some text in a secret message that only if you know how to decode it can you read this message. So the way this little problem works, say we have an example sentence called, "If man was meant to stay on the ground, God would have given us roots." Now I need to make that into the best square I can. So rows and columns, if you see this, kind of arranges them in a fashion that leaves the bottom row with not too many missing characters. And then once we have it that way, we need to read down the columns like this, so that each word of the coded sentence is going to have, like, that's the first word right there, and then the next word is going to be that one right there, and so on. So the resulting encoded message here is going to look like that. That's our job right now. We have to figure that out, okay? We're going to use Ramda to do it, and I've already broken this problem down into several smaller problems that we'll need to solve, and then we'll use the smaller pieces to solve the bigger problem, which is typically how you would approach a problem. So here we have, this was in the problem statement already, and then there's 3 more sentences just to make sure. These are all the inputs I want to work. And then these are the correct outputs if the code works. So these are going to help us assert that our code is doing what we want it to do. So the very first job we have is we need to clean our input. So let's say I have this string in my hand. It says hello, exclamation, exclamation, space, space, a lot of periods, a lot of commas. We just need to strip that out and make it a lowercase hello. So I'm going to take that and I'm going to pipe. If I use the to lower, I can get it down to a lowercase hello, and I'll pipe that into the replace, where I'll use regex to just find spaces, spaces, and then we'll take out periods, we'll take out commas, we'll take out exclamations, make sure it works on the whole string, and we're going to replace those with nothing, and that will clean our input for us. That's an easy pipe through. So I give it any string, it'll make sure it lowers it and strips out the punctuation and spaces. Okay, so then the next thing we need to do is we need to figure out how many columns go into our square. And that one, just because there's an easy way to do that, I've given us a hint. If we take square root of length, put that through the math.floor, use that as our rows, and then the columns end up being that divided by, or our length divided by our rows. And then the focus, I didn't want to be on this little algorithm, so that's why I gave us a hint. But the pipeline could be cool. So let's say we have a pipe. Actually, I need to first take some input, and then once I have input, I need to take the length. I'll just grab the length off of that. Now, columns for is going to be a pipe for me, and I'm going to return columns for the length. What am I going to do with the length? I'm going to pipe it first through math.square root, and then I'm going to take that through math.floor. I'm going to take that through divide by the length, and take it finally through math.ceiling. And hope I didn't spell that right. And then so this is my little pipeline that takes one thing through the following methods. And I can tap at each point if I need to, just to see. So if I tap at the beginning, it's the numbers, or those are all the lengths of my strings. Tap after the square root, you can see the square roots. Tap after the floor, you can see it drops them down to the integers. Tap after the divide, you can see what it does. And then finally after the ceiling, and then, ooh, I missed a comma. Okay, and then we end up with our answer that we want. So that's how I would do that one. So then we have the determine number of columns method working. So then our next job is we need to be able to turn something into a square. If I just have some text, I want to make it into the best possible square or rectangle that it can. And we have the tools that we need to do that job now. So here's our method. The input is have a nice day. The output should look like that. Let's just be able to split it. This one's actually pretty easy, because if I know how many columns I'm supposed to have, I can use Ramda to split every number of that. It'll just take, it'll find that many characters and it'll move to the next row. So that one's not too much going on there. We can get that output that we want. Then, because I'm setting myself up for a zip, I don't know if anyone's familiar with functional programming, you may have heard of the zip method before. But if you have two arrays and you want to pairwise get the elements matched up, so like the first element of the first list and the first element of the second list together in a pair, that's what zip does. And because I know that's what zip does, I'm setting myself up to use zip to solve this problem. But I have one little gotcha, and that is these uneven rows would be in the way. If I have feed and then aug, if I zipped this, I would get the FT and the O, I get the EH and the G, but this guy wouldn't work because there's no character down there to match up with, and so he'd get dropped. So what I'm going to do to get around that is I'm going to pad in some extra spaces. If my square is not perfect, then I'm going to put spaces in to make it perfect. So that means that if my input looks like that, I want my output to look like that, where I just added 2 spaces onto the OG so that we have an even number of items in the columns there, so that I can use zip later. And I'll show you that. So okay, this one works. I need to let's see, map it. If I mapped it with identity, it would just be the same thing that it already was. So, right, I need to know the number of columns first. Okay. If the row is already the length of the column, then I just want to leave it alone. That's fine. But if it's not, then I need to fill in the number of spaces that I want. So I'm going to say, I use the r.ifelse method, which the first thing you hand to it is the function that's the condition. And if it passes the condition, it'll run the next function, which is the next argument. If it doesn't, it'll run the other one. It's kind of like just any if else you've ever seen in your life, but it's the Ramda one. So let's see. So if I need to check the row is what I'm getting. So I'm going to pipe the length of the row into whether it equals the columns or not. That's my condition. And then if it passes that condition, I want to leave it alone, which is the identity function. If it doesn't pass that condition, then I want to do something to it, which is this function right here. So let's just set ourselves up so we can at least see what's going on in there. So this is where we're going to do our work, is inside this function right here. Because when the row is already equal, we don't care to work on it. We'll just pass it on through. So I would take, let's see, I need to be able to fill the spaces, or fill spaces into this thing. So I'll go ahead and pipe just for the row. I'm going to take, I need to figure out the difference between the columns and the length of my row. So I'll take the length of my row into subtract the columns from it. So that's going to be the difference. And then now I need that many spaces. So I'm going to do a times on an always a space. And I'm going to get back an array of that many spaces. And then after that, actually, let's see where we're at. Let's see how that's going. Here, let me show you the taps again, so you can get a better idea. I guess they're off the screen. The length was 2. If I subtracted the columns, it was again 2 because I had 4 minus 2 is 2. Then I take the now I have this array of spaces, but now I want to, that's the right number of spaces. I'm just going to concat the row as the beginning part of that. And then I need to join it back together. Space. And did I get it? Let's see. Oh, I need to fill spaces on the length, right? Or wait. Oh no, I did. I'm on to the next test now. I forgot. Sorry. That one's passing. We just need to go transpose the square next. So this is my little pipeline that does that. And my style is usually make a pipeline, give the pipeline a good name. If you find any of this illegible, the general step to take is to take one of them, pull them up, and give it a good name. And then you're piping things that are named well together, and then that's easier to read for someone else. But if it's already just, if it doesn't make sense to you to do that, then don't do that, or yeah, however. But I tend to just make a pipeline that does the job and then use the pipeline on the inputs. So that's our filling a square. Oops. We're going to transpose a square. If you recall what transpose does from like, if you've done like matrices, whatever, you transpose them, you got rows and columns. You just want to kind of like flip it up and over so that the rows become the columns and the columns become the rows. That's kind of our job here, because if you recall the problem statement, we have text that looks like this, and then our job is to grab it and take the columns as one row, and then the columns is another row. So that's why I'm calling it transpose. And let's go ahead and do that. So to transpose this, I'm going to use a reduce. And actually, I'll be a little fancier, and I'm going to use a converge. And some of these methods, if you go over to this Ramda site on the docs, every single one of these methods you're seeing me just use are documented here on how to use them. And as you use Ramda more and more, you'll just have seen these methods enough, and you'll know what they do. And then you might see the right time to use them, and then be like, "Ooh, it's time to use, converge for the first time." Feel excited, but otherwise, you might find that the code's illegible to your teammates. It's up, it really is the comfort level of you and the people around you on what you think is readable and maintainable. But I've been doing this enough to just be comfortable with some of these functions, and so when I think of a time to use them, I'm like, "Ooh, let's use these." So I'm going to use a converge because I really want to do a reduce, but the seed to my reduce is not simply just the first thing that'll come in. I need to work on it a little bit first. So I'm going to take a pipe. I'm going to be handing it an array that looks like that. And so I really want to seed it with the first row, but kind of work down a little bit. I'd rather have, instead of just a string that says have, I'd rather have an array of characters, or an array of characters, where each individual character is inside his own array. Because when I have it in that form, I can then easily take those arrays and zip them with my columns as I scoop across. And you'll see, I'll show you the output as we do this. So I'm going to take the head, which is the first item in the list, and then I'm going to map the head with the of function which just just takes whatever it gets and puts it in an array. I have a string of characters, so each character is going to come through this and get stuck in his own array. When I'm done, I'll have an array of arrays of characters. So like a two-layer array is what I will have. And then the list I'm going to work on is the tail. If you've done functional lists before, you usually break them up into head and tail, and then you can recurse over them, some of this stuff. So, and then once we're in there, we'd have our function where we'd have an accumulator and the row, and we'd work on it. I'll just return the accumulator for now. And you can see my output. You see how I have an array of H, A, V, E, have, going down the side there. On the right, you can kind of see this part. That's what I'm currently working with. So now that I have that, it's not too hard to zip with the accumulator pipe. I'm going to zip row. Okay, so I'm going to zip with the accumulator just to show you what that gives me. Is now I have this, there's kind of like some deeply nested arrays going on here, but the characters in them are the right characters that I'm looking to get next to each other. So after that, I could map it with a flatten, and then that'll at least, you know, drop that second layer of arrays. So now I've got these characters together. I'm even closer, but not just flatten. If I pipe the flatten into a join, then it works. So what I had, see, I had an array of characters. Well, if I join those characters into a string, then now I just have a string that's like HAE the string and AND the string, which that's exactly what I wanted. So that's how I would do that one. But again, so like some of this stuff, just comfort will come over time with using the library. And then these techniques apply in other functional programming languages too, because you'll recognize some of this stuff just if you've ever worked with functional lists before. So now let's keep going. My next test to pass is I need to be able to transpose uneven row squares. And that one doesn't work because I end up with extra spaces on the end, and I don't want them. But I can just go fix that real quick. Because back over here when I was joining, I could just end it in a trim, and then that'll strip my spaces off. So, and then if you needed, let's say that all that together was too much, I could just put, you know, give this a good name, be like flatten and trim, and then you could just take all of that out. Oh, I guess that would be a pipe. That. So the general goal is, or like, introduce good names along the way. Oh, another interesting thing is too is that doesn't necessarily have to be defined in scope there, because it doesn't use anything from the closure. I can move it up and out, and it still works. I can have it up in a library of reusable functions that I just use a lot on other things. So if you ever solve a problem and it doesn't rely on exactly the state that you had it all in one place when you were solving that problem, you can just reuse that function anywhere, right? So that's the idea with these functional pipelines, is that you don't want to rely on any outside parameters, like no global state. You can't reach up to some global and use it. If it didn't come in your function, or it's not in a nested function that has a closure open on some outer functions variable, then don't touch it, is the rule. That way your functions stay in a way that you can rely on to use again somewhere else. And another thing about functional programming, I guess, is you don't ever mutate your incoming parameters too. You want to stick to immutable stuff. And the Ramda library, if you've noticed, we're just working with arrays and objects. They don't have their own special data type or anything. So it is possible for you to mutate this stuff. If you do it, it's not going to stop you, but you don't do it, I guess, because the benefits of some of this functional programming approach are really just by, if you have this guarantee that if I ever give you a parameter, you're not going to touch it, If you're going to use it in some way to give me an output, you're going to either copy or clone that thing and then use it. That's really where a whole world of bugs are avoided. It's just don't mutate stuff. So we're almost done with this guy. So let's see. Now we're on the last step to encode some inputs. There's a lot to go through. I'm going through it kind of fast, I know, but I wanted to fit it into our Lunch.js session, which is only 45 minutes. So I'm going to put this up on GitHub too, so if anyone wants to go back over some of this, and I'll leave the challenge unimplemented, and I'll have the solution with it. So you can try to take a stab at it on your own with Ramda, and if you want to check what I did, you can go look at what I did with the solution, and I'll have that up. But now that we've done all these little steps, we can use them to solve the bigger problem, which is to encode our input. So if I tab my input function, and we'll just return that input for now. Okay, first thing, I would need to clean the input. We know how to do that now. So if I have cleaned input, that would just be my clean input function that I wrote up there on the input. I would also need to know the columns that I'm going to break into for my square, which we know how to do, so we've made that method. So I got my determine number of columns for that cleaned input. Okay, and now I'm ready to do my pipe. I have my code input pipeline that I'm going to run on cleaned input. Now I'll just use identity so it can make a pass. Okay, the first thing we were going to do is we need to make a square. Is that our first step? Turn input into square. Yeah. Here we are. So I need to turn into square, or turn into square, and then that took the number of columns, and that still returns the function that's going to do it. And then the next thing, after I have the square, is I need to fill that square also by the columns. And then once I have the square, I want to transpose that square. And then if you see where I'm at now, I have an array of those things. And once I've transposed the square, I can just join it with space. And yeah, looks like that passes. So let me put the only on there so you can see that. So this is what our pipeline turns into to solve that problem. And if we've already solved all the little problems, then solving the big problem is easy, because we can just pipe all the stuff through our methods that we made for ourselves. So that's encoding, if you remember these inputs up here, that's making them into these outputs right here. And then we need to go the other way, which is to decode these things. So let's do the decode, which is last. Take that off on the only. Okay, and because we've already done the work to encode it, decoding it, we can reuse a lot of our methods, which will be cool. So I'm going to get some output, and then turn it for now. Okay, I will take all this decode output. I'm going to split it on the space, just so you can see now I have this array where I've at least got them ready to work on. I need to transpose again. I already solved that problem, so let's reuse that method. But I would need to know the length to do that. So if I have a row, give me that row's length. Actually, in this case, this is the array of stuff. So let's see what's coming out there. I've got this array of stuff, and I want to make sure what's the length. I won't even use Ramda right now. I'll just grab the length off it. I'll show you what you can do with Ramda in just a second. If I knew the length, then I could go ahead and I just need to fill the square. So I'll go ahead and fill that square with the length, and then I'm doing it on that row. Okay. Maybe do you see the subtle difference between the output? Yeah. Some spaces. So that was my goal, was to get those spaces there so that I can then freely flip this or transpose this thing with my zip. Because the thing about zip is if I have uneven length lists, it's going to stop at the shorter one and it's going to drop items in the longer one. So that's why I'm working to keep them the same length so that I can take advantage of what zip does to just solve this particular problem for me. So and once I have that, and then I can just transpose it. And now they're flipped. And then once they're flipped, I just need to join them back together with some spaces. And now we're done. And that's decoded what we encoded before. So we can go to and from with this square code implementation. Now this thing, if you want to see a crazier version of it for fun, because otherwise we're just going to go to questions and talk about stuff, because that's all the material I have for you. But I'm going to go ahead and try something, and I'm going to converge again, because I like converge. And I'm going to use the call method. Call lets me build the function up on the left path and then invoke it with the arguments on the right path, which is interesting. I think so. Because I need to figure out the length. So if I pipe the head into the length, that gets me the length. And then I needed to make that fill square function. So we'll pipe that into fill square. And now I have a function that'll fill a square for this length on the left side. And then I want to invoke it with the original item, which is just identity. And then it does the same thing. That's what you just saw that method right there doing. But arguably harder to read. So I wouldn't do this unless I was trying to be mean to somebody. But again, comfort of the team on what, if you've seen this stuff and this stuff is comfortable to you, then by all means use it. But the functional style is not typically one that is wider adopted in shops, and so might seem alien and weird. But just hopefully, my goal today anyway was to show you, if you have to do work on some common problems, this is what it might look like if you used Ramda. This is by no means the only solution to the problems that we've done. And I know it went a little quick, but the idea then is build up pipelines, have reusable functions along the way, and yeah, that's pretty much that. So anybody have any questions about this amazing amount of material that was thrown at you very quickly? Yes, Steve.
You used always a couple times. I just wasn't sure the exact, I might have missed it, but the exact reason for using always function.
Oh yeah, so always is a function that if you invoke it, will always give back what you told it to. So it's kind of like a constant function where regardless of arguments it receives, it'll just answer back with that one thing that it knew about from back when. So I used it in the times right here. Is that what you're talking about?
Yeah.
And in that sense, because I need to figure out the difference between my row length and the row length of most of the rows in the square. I'm like the odd one out by having like 2 less than the total that I should have by being the bottom row of that. Remember this feed the dog. Dog needed 2 more spaces to fill them out. So we figure out how many to do. Times will run that thing as many times as you tell it. So the 2 is what's coming into that. But then times needs to know about a function to run. And that's why I'm using always space, because it's going to invoke that function twice. And that function is going to hand back a space twice and give me an array of all the answers that were in there. So by the time this guy runs, I'll have an array of, so here, let me go back up here. Let me just tap right after that. You kind of see I've got arrays of the amount of spaces that need to go in there, which is why the next thing I do is, well, I guess I can cat them first. And see, then I've got these arrays of characters where I've got extra spaces on the end. And then my last job is to join them all into one string. So you could just, I guess, do that in other means. Oh, what happened? I think I lost the presenter or the projector. Yeah, probably is. Are we up to time? How's our lunch time for 45 minutes?
Look like Q&A.
Yeah, okay. Yeah, just only Q&A for now then, for sure. So that was that one. Did I answer your question, Steve? Okay. And any other questions? Anybody? Yep.
How does Ramda handle errors? Like, for instance, if one of these pipelines breaks or causes an exception, what's the best practice for dealing with that?
So I guess you can be caught with some obscure things. If you see and you're like, oh, I have this message that doesn't really tell me what's going on. I'll use tap a lot. You can harden up your functions against common errors with, like, say I'm taking a property like the r.prop. They have also r.prop or, which will default to a default value if whatever that property isn't there. So then you can set your code up in a way that will just fall back to sensible defaults to then send on through your pipeline. But if you've set up a pipeline and you're just getting a weird error message, then my first step, I start to tap at each point in my pipeline to try and see what's going on. But once you have the pipeline working, you can, I guess you just kind of test it against the inputs you would expect. But yeah, like any other code, I guess it could throw if you didn't fully consider all of the possible range of inputs and that kind of thing. So you still do have to be on your guard for that. But there are a number of methods that will at least fall back to safe defaults so that you're not just caught unawares by like an undefined property or something like that. So, but yeah, that's how I deal with it anyway. I have oftentimes been like, what is this error message? And then like have to break my pipeline apart and then figure out which step was breaking, and I go harden that one up and then put it all back together. But then once I've done that a couple of times, I just start to, if I expect certain inputs and just try to scrub them, I guess, in a way that's sensible so that they can't be bad. But can never get them all, I guess. So there's always that chance. But how about anyone else? Question? Oh, yeah.
So that last example you did, there was kind of the easier to read version and then the straight up functional version. Are there performance benefits to kind of maintaining kind of a more functional paradigm in there or not? It kind of depends. Like,
I wouldn't say performance benefit. I mean, it's creating a bunch of functions that then have to get run in order to like do their thing, which you might just be like, I can just get one method that just does it and like avoid allocating all these functions and doing all this stuff. So, but the reusability of it can be extended a little bit. Say like if I have a function that doesn't really rely on all this state around it, or maybe I have some parameters to a thing, but I'm not ready to hand it this one parameter yet because I know I won't have that for another, some asynchronous call to go get it. Then by having a function that can curry the arguments like this, I can freely hand it the ones I already know about and then delay the arrival of the other parameter until I get it. And then the function also runs. Whereas that might be harder to orchestrate with just traditional function, I guess, because you'd have all these dependencies on expecting the step to be there already. So that's one thing. As far as execution time or anything, I wouldn't say that you're getting faster speed out of one versus the other. If anything, the imperative approach might, in some cases, get you more speed. But the idea, I guess, is what you sacrifice in, because you might be allocating more objects in the functional style, because with the immutable discipline, rather than mutate something and keep all your memory the same and all you did is swap one little property on it, instead you're reallocating another object, cloning that thing, giving all its properties to the new guy. You could call that, but the expense of object allocation is pretty trivial, I guess, these days. And the benefit that you gain in avoiding a whole range of bugs that you might get by just having some state that you monkeyed with before that isn't quite right for your function to run on yet. The immutable approach can ensure that you never mess with the parameters. So then there's some mentality there, I guess. But again, it's just a style versus style thing. I wouldn't say it's better. So, yeah.
Does Ramda have like built-in immutable data structures, or does it like work nicely with other?
It'll operate on whatever you want, but it works fine with JavaScript arrays, and objects are the default data types that we'll use. They didn't try to make their own immutable types for this. But say you wanted to pair this with immutable JS, that would be fine. You just use all immutable JS types instead of arrays, wherever I was using arrays. and you'd have to use their library's methods to clone those things and whatever. But they have a large number of convenience functions to work with regular JavaScript arrays and objects. So like this associate method, for instance, will take whatever you hand it and then tack on this extra property, but it doesn't mutate this. It copies and clones that with the new property. Same idea, like you've seen the extends or the merge method a lot. I mean, there's one of those in here. So if you have a bunch of objects, you want to object that's got all the properties and the values on it, merge will clone or create a clone for you with all that stuff mixed into it for you. So there are methods here that enable you to just use the built-in data types. But if you kind of stick to a certain discipline, you can stay immutable. It's just that nothing's stopping you from reaching in there and changing some property to some other property. It's not going to yell at you. So you just don't do that, I guess. Or that might be a bug someday. Or maybe you can justify it to yourself and sleep well at night. That's okay. Yeah. Okay. Cool. All right. Yeah. Thanks, guys. It's fun.
Thank you,
Let me
John.
know. Yeah.
Thank you.